Welcome back to the workshop. We want to continue taking a look at section 7.5, strategy for integration. And in this section, we're just discussing what method should we use to perform or to find the integral, right, to perform the integration. All right. So the first time I wrote these notes up, I didn't have examples. So if you were to open up the lecture notes at this time on Blackboard, you would see that there are, in fact, these functions written. That's true for 1, 2, 3, 4 examples. It's worth also mentioning that the practice problems have been updated to include, of course, some practice problems, not just to be determined, but also it appears that I forgot to begin section 7.6 on a new page. So you'll want to go ahead, but you don't need to do anything. We'll start off here. We don't need a lot of room, and so that's okay. But on the new notes, I did put that on a new page. All right. Also on Wednesday, we're going to take a look at section 7.6, integration using tables and computer algebra systems. We're primarily going to focus on computer algebra systems. We're briefly going to mention the tables. Tables are a bit tedious and quite annoying and almost useless when we have access to a computer algebra system. It makes quite a bit more sense. Of course, being able to recognize how to use the tables would certainly be good. All right. So our first example, if we want to follow through with what the strategy outlines for us, our outline strategy, we would simplify the integrand if possible. Can we simplify it? Theta times inverse secant theta, right? Inverse secant, that is not 1 over secant there, secant to the negative first, that is the inverse of the secant function. So this is an inverse trigonometric function, also known as a transcendental function. So since it's a transcendental function, we might immediately then skip to part 3, right? Step 1 is simplify possible. There's nothing to simplify there. Step 2 is look for an obvious substitution. I don't see anything that's obvious. Maybe you would want to say let u be inverse secant theta. Try it. Probably not going to lead you anywhere. Okay, so you move on. Step 3, classify the integrand according to its form. Well, this again has that inverse secant, so it has a transcendental function, and by part C of our step 3 there, that says to use integration by parts. So here, observing the information or observing the steps that we were taking a look at, we would then use integration by parts. Right, that's just looking at the strategy for integration to help us decide what to use. So you might ask yourself, well, does that actually work out for us? And I can tell you, yes, integration by parts does work. So the interesting part of this example, integration by parts does work, but leads to a trigonometric substitution. So that's a little bit interesting. The integration by parts does work, but it leads to a trigonometric substitution. All right, interesting. So that's how we would approach that problem. Let's see. Yeah, I'll let you take a look at that if you want to in our supplemental video. For the next example, we have x plus 1 divided by x squared plus 4x plus 8 squared. So we go again to our strategy, our outline strategy. We simplify the integrand if possible. Well, something that you could do, right? You have a polynomial divided by polynomial. When it tells you to simplify and you have polynomials, one thing that you can do is factor the numerator, factor the denominator, and say, all right, do I have any common factors? Simplify. None in this case. The denominator has a quadratic that's being squared. Is that quadratic factorable? What multiplies to 8 and adds to 4? Nothing, right? 1 and 8 multiply to 8, that doesn't give us 4. 2 and 4, that doesn't work. And that's it. right? Those are our options for multiplying to 8. So we say, okay, that doesn't work out. It doesn't factor. Even if you were to, include the use of radical coefficients, yeah, maybe then you could get something, but a little bit annoying. So fine. You say to yourself, I can't factor it nicely. There's no common factor, certainly not an x plus 1. So I can't simplify. And we spent way too much time thinking about it already because we want to be moving on, right? In terms of homework, we don't want to spend too much time on. Exam, we have a limited amount of time. So we want to think about these things relatively quickly. Does it look factorable? No. What do I do? Move on. Step 2, look for an obvious substitution. So sometimes you might say to yourself, all right, the quadratic in the denominator, linear in the numerator, take the derivative of the denominator, or actually, take the derivative of the denominator, see if the numerator is the derivative. In this case, we have it squared, so it wouldn't exactly give us that natural log that we're looking for in that idea. But we can also ask ourselves if what's inside here, if the derivative is the numerator, because that could still give us something of the form 1 over u squared du. And that would be nice too, right? That would be maybe an obvious substitution. So you check for it. Derivative of x squared is 2x. Derivative of 4x is 4. So the numerator would have to be a multiple of 2x plus 4 because the derivative of 8 is 0, right? So we would need a multiple of 2x plus 4. But if I pull out that common factor of 2 to get x plus 2, it's x plus 2, not x plus 1. So the derivative is, right, the numerator is not the derivative of the denominator. So, okay, what do we do there? Well, that didn't help us a whole lot. It was missing just 1 here. So we could start to manipulate, right? If you wanted to go on to step 4, where you manipulate the integrand, you could manipulate it. So that way it was an x plus 2, and then do a minus the integral of 1 over this thing, and then see where that leads you. That is actually one possibility, and that possibility is very related to where I found was a beneficial direction to go. So, okay, nothing yet. Nothing yet. So no obvious substitution. So we classify the integrand according to its form. Let's see, is it a trigonometric function? No. Is it a rational function? Yes, it is polynomial divided by polynomial. So you might say to yourself, use partial fractions. Can we use partial fractions? With that denominator being, let's see here, with that denominator being a quadratic, being squared, quadratic is irreducible. That fits nicely some directions that we have for integrate partial fractions. So one thing you could use, or you could try, is partial fractions. Let's see here. I think that is not the direction that I went. I went a different direction, but you could try partial fractions, and I think this would actually work. This could work. And this could work nicely. I think once you attempt partial fractions, what you would end up with something that still requires another method, right? Because it's going to have something divided by this quadratic plus something divided by this quadratic. So no matter which way you go, you're having to integrate something with this quadratic. So you could try partial fractions and that will lead you somewhere. The other thing that you can try is recognizing that no matter which way you go, you're going to have to deal with this denominator. So you could use something a little bit different. And this would be, well, actually, let's follow through with our strategies for integration. So we try integration by using partial fractions. It could work. In fact, it definitely will lead you somewhere. You'd be more than welcome to give that a shot. I think you would find, actually, no, I'm not quite sure what you would find, because again, that's not the route that I went. So integration by partial fractions would work just fine. Integration by parts, not really. I don't think that would really lead anywhere in this case. You could try it, and I definitely think that could lead somewhere. If you wanted to differentiate x plus 1 and then integrate 1 over x squared plus 4x plus 8 being squared, that actually could work out really nicely. Could, because that would give you something that involves transcendental, in which case you would apply integration by parts again. But I'm focusing on this quadratic, right? This quadratic is what really stands out to me. So what stands out to me about this quadratic? Well, what stands out to me about this quadratic is its form of x squared plus 4x, this number being a nice even number. So what I can do is I can recognize, I can notice that I have x squared plus 4x plus 8 is equal to x squared plus 2x, sorry, 2 times 2x plus 4 plus 4. So 2 times 2, oh, sorry, 2 times 2x, this identifies for us a b value in the idea of completing the square of x plus b squared, x squared plus 2bx plus b squared. So this is our b value, this is b squared, but it can be written as 4 and 4. So this in fact gives us x plus 2 squared plus 2 squared. And when we recognize that, we could then recognize the denominator as the square root of x plus 2 being squared plus 2 squared raised to the 4th power. So now we have something that actually suggests, right, by rewriting, this would be step 4 if you really wanted to call it that, manipulating the integrand to make an observation, to observe it as this, which would suggest the trigonometric substitution. And almost no matter which way you go, you're going to be forced into this situation. Okay, if you use partial fractions, eventually you'll have a denominator that you have to make this observation with. So you can use this, which would recommend the u substitution. Let's see here. All right, this would suggest letting x plus 2 be equal to 2 times the tangent of theta. And again, right, that x plus 2 doesn't quite work in the numerator. So if we add 1 and then subtract 1, we get a x plus 2 to give us 2 tangent theta minus 1 in the numerator. So that's how that would pan out. So 2 tangent theta minus 1 divided by 2 tangent theta squared plus 2 squared, square root of that to the 4th. And we can simplify and perform the integration. So that's the way that I would recommend going. That's going to be useful. There are several steps in that integration, though, several manipulations there. All right, so another example here, what we do, let's see here. I thought we did this example in a previous section, but it appears that this is right here in front of us right now. So I said that we could, well, let's look at our questions here, look at our strategy. Step 1, simplify the integrand if possible. I don't see anything that seems obvious that would want to be simplified. I don't see a common factor in the numerator and denominator. All right, fine. So we look for an obvious substitution. Is there an obvious substitution? I don't really see one. Sometimes it's nice to have the denominator be u, so you could try that. Try u equals x to the 1/3 plus 1 and see where that leads you. It might lead you somewhere. You definitely have to do some manipulations in terms of you don't have du obviously right there, so you'd have to introduce the appropriate factors, divide by the appropriate factors, and then right, work through that substitution. So I think that might lead you somewhere, but maybe not somewhere that's to a significantly easier integral to evaluate. All right, so we classify according to its term. Is it a trig function? No. Is it a rational function? It's not polynomial divided by polynomial, but it is, right, x to a power divided by x to a power. So it's kind of looks like a polynomial rational function, kind of, not really, because it's fractional exponents. So we say, okay, let's move on, just double check. other methods. Integration by parts, is it product of a polynomial and transcendental? No, not really. Okay, so next one, radical. Does it have radicals? Yes. Okay, so we try a substitution, trig sub. No, none of those are really where we're at right here. We don't have the square root of something squared plus variable squared, or something squared minus variable squared, or variable squared minus a number. So we don't really have that situation. What do we have here? Well, that's why this example is fantastic, right? This is maybe something a little bit different. So you try your U substitution of x to the 1/3 plus 1, and maybe it works, maybe it doesn't. That's fine. We try various methods. This one in step 4, where we manipulate the integrand, this is something very useful. So this is actually reaching way back to essentially like what would be not even Calc 1, pre-calculus content. Sometimes you would come across the scenario where you have something like, let's call it x to the 1/4 plus 2x to the 1/2 plus 1 is equal to 0. They would have you solve equations like this. How can you solve this? Oh, okay, yeah, how can we do that? Well, what you would have to observe is that this is x to the 1/2 being squared plus 2 times x to the 1/2 plus 1 is equal to 0, allowing you to observe that this is a quadratic equation. So observing how these exponents can relate to one another can be very helpful. And so the manipulation that I would encourage us to make in this case would be to recognize that if we were to consider a common denominator for 1/2 and 1/3, it would be 1/6. So if we rewrote this where the exponents have a common denominator, this would be x to the 3/6 divided by x to the 2/6 plus 1 dx. So then, does that really help us? How does that help us? Well, what we can do is we can recognize then, let's see here, is that what we did? Nope, okay, that works out nice. 3/6 divided by x to the 2/6 plus 1. If we were to then say we have x to the 1/6, that would be cubed divided by x to the 1/6 being squared plus 1. So if we were to let u be equal to x to the 1/6, then we would end up essentially with something that's polynomial, right? We would end up with x to the 1/6, we would end up with u cubed divided by u squared plus 1. We have to handle the du here, but we could do that, right? Du is 1/6 x to the negative 5/6 dx. So we'd have to introduce a factor of 5/6 in the numerator, so that way we could also look at having an x to the negative 5/6 or x to the 5/6 in the denominator, however you want to think of that. But when we do that, that still is easily replaceable by u because it's a power of, right, x to the 1/6. Would be u to the negative 5th power. And then the factor of 1/6, that's easy, right? So we could perform that substitution, and that would provide for us something that looks like a polynomial divided by polynomial, and we can go ahead and implement integration using partial fractions. So that's essentially what we would want to do there, and that would provide us what we're looking for. Looks like maybe I didn't even use well, it looks like I used a second replacement to make things even easier, but it doesn't really matter. Anyway, so perform this substitution and that will lead somewhere. Maybe not somewhere super obvious. I performed a second substitution. It looks like you could simply perform the polynomial division in order to apply that. Actually, no, because you'd end up with u squared plus 1, which doesn't factor. So you'd have to take care of that. Anyway, so it's interesting. I'd encourage you certainly to take a look at that. And then for our last one, okay, excellent. Our last example that we want to talk about. How would we approach this? All right, well, what do our techniques say to do? Our technique says simplify if possible. What would we simplify here? Well, we notice right away that it's sine of x and cosine of 2x. So one thing that you could do that would make sense to do in terms of simplifying right away is to write it all in terms of x instead of 2x. So you could do that, and that would make a lot of sense to do. That would be a very valid simplification. So in this case, cosine of 2x has many different forms. Cosine of 2x. Cosine of 2x can be written as cosine squared minus sine squared, 2 cosine squared minus 1, or 1 minus sine squared. Now, this is sine, so I might say, let's make everything sine just to start off. No real good reason other than that's what I'm choosing. You could choose any one of these 3 variations of cosine of 2u. So you might use 1 minus 2 as sine squared u. So you might make the simplification of sine x plus cosine of 2x is, what did we say that was? I forget quickly. 1 minus 2 sine squared. All right, 1 minus 2 sine squared x. So now it's just an integral with regards to this, all right, with regards to sine of x. And one thing that's a little bit interesting here is that we can then look at this as negative 2 sine squared x plus sine of x plus 1 being squared dx. And all right, the first place that I go to is I see a polynomial in sine. So I would first think, hey, let's do a substitution of let u equal sine. So that way we have 2u squared plus u plus 1 being squared. It's the integral of a polynomial, and that's really easy to do. We can even expand it, right, because it's being squared. The problem there is we don't have a cosine x for the du, right? Du would be cosine x dx. And so that actually doesn't work out. We would say, oh, shoot, that obvious substitution that you may have thought of, that's what I thought of at first, doesn't work out, okay? As obvious it was to make that substitution is how obvious it was that it was also not going to work. So I said, oh, okay, and I move on. So I don't see any obvious substitutions. So then we classify the integrand according to its form, right? Our second step, is it a trigonometric function? Well, in and of itself, it is not an individual trigonometric function. Oh man, so is there something different we could do? What would we do if it was different? I'm not really sure, but I don't want to multiply that quadratic out, right? I don't want to multiply, I don't want to actually square this thing because I'm lazy and I don't want to do that. So the first thing I'm going to do is double check for any other methods. Because if I want to observe it as just trigonometric functions, then I have to split it up, the integral of this trigonometric function or the product of these trigonometric functions plus the integral of, right? Because I don't have the ability, I don't have a good ability to handle these sums of trigonometric functions, but I do have the ability to handle products of trigonometric functions. So I move on. Is it a rational function? No, not going to apply partial fractions. Integration by parts. Do I have a polynomial times a trigonometric function? That is a transcendental function. No, I don't. So integration by parts doesn't quite look like it's going to fit super nicely here. Excuse me. So then we move on. Is it a radical? No radical. So nothing in our classification fits nicely other than these are a bunch of trigonometric functions. So I say to myself, I've got to multiply this out. So you multiply this out and what do you find? Well, you find something that's large and doesn't necessarily look super pretty, but it's just a bunch of trigonometric functions. So you multiply that out and you get several powers of sine. Okay, several powers of sine. When you have several powers of sine, right, if you end up with a sine to the first power, you integrate nicely to cosine. That's going to be in there somewhere. You've got that constant in there. Integral to constant is just x. That's no problem. But then you get a bunch of even powers of sine. So you use the power reducing formula, sine squared is 1 minus cosine 2u divided by 2. So we say, all right. So we used this formula actually to get rid of the cosine of 2u, and then we're going to end up introducing it back in, right? So we use these power reducing formulas and we integrate appropriately. But I believe that's the best way to go for this problem at this time. I didn't find another way to go. Is there another way to go? Quite likely. I would not be surprised one bit. I like to, for example, when I actually started, I multiplied this out rather than multiplying out this because this has fewer terms, and then started making substitutions or using power reducing formulas rather. So it depends. So if we review here quickly, in our first example, integration by parts makes sense. Polynomial times transcendental function. It does work. It leads to a trigonometric substitution. For our second example, we said, all right, we have polynomial divided by polynomial, so we could try partial fractions. And I do think that that would actually lead somewhere. I don't know why I didn't take that route, but I ended up manipulating the numerator so that way I could observe our denominator as well, manipulated the denominator to look like this and use this substitution. And this substitution will work. For our third example, if we were to look at this as x to the 1/6 being cubed divided by x to the 1/6 being squared plus 1, recognizing that u substitution does in fact give us polynomial divided by polynomial, is right looking for that integration using partial fractions. It works out that the partial fractions itself doesn't necessarily work. However, having that polynomial divided by polynomial does make things look a little bit easier, and it is we're able to handle that as polynomial divided by polynomial. So then we say, okay, that works. And we find our last example of what works here. Well, no obvious substitutions. We move on. Trigonometric functions. Okay, nothing crazy, just a little bit of work to multiply things out and apply our trigonometric function integral methods, right? And that's it. That's it for the section. So I know that's quite a bit. Again, I'm going to post videos of each of those being evaluated, but I think the discussions themselves on how to approach it is just as valuable, if not more valuable, than the actual calculations of the work to find the evaluation of that integral. So thank you for your time and your attention. If that's all that you watch for this section, I give that a thumbs up. If you need more examples, watch the supplemental videos in which we actually go through those calculations. Have a great day.